Hi, welcome back. So I'm not sharing screen. I know that because I forced you to watch my beautiful face every day for 5 minutes. That's your punishment for attending this workshop series. So let's talk about last week. Uh, what did we learn last week? Okay, I'll start, take a step back. Are humans intelligent? Okay, is ChatGPT intelligent? Some people said it's intelligent, some people said it's not. Oh, by the way, today we have candies for people in person for answering questions. So it's more incentive for people to come for the in-person classes. If I can figure out how to open this. Oh, I'll let you guys open this and give it back to me though. Okay, so last week we were thinking about how does intelligence work? How do humans think about intelligence and things like that? And we also saw like there was a tool we saw from Hugging Face. Does anybody remember the name of the tool? So last time we went, if you remember, we went to Hugging Face and we the first line we wrote was import something. What was it? It's okay, take your time. You don't have to, it's not a trick question. Transformers. Okay, I got an answer from the chat window. Yes, transformers. And to remind you that, so I will give you a virtual candy. Okay. I will show it to you. This is your candy, Ramesh. I'll give it to you online. I'll send it to you as attachment. Or I'll give it to one of the people here and they can eat it on your behalf. So yes, transformers is what we saw last time. And we had seen a couple of basic examples of, let's say, sentiment analysis, where you can give your sentence to transformers and it will tell you what sentiment it is. We, what do you remember which tool did we use for that? Like in Hugging Face, we had used something to connect with all these transformers. Pipeline, perfect. Okay, pipeline. Candy. Okay, perfect. Nini, you stole like two already, so you should give it back. Okay, so last time we saw pipeline, transformers, and things like that. So this time I want to start with this question. Do you think humans are intelligent? Yes, okay. How does a human child learn a language? What happens to the child when it's growing up? Give me a second, let me lock the door, close the door. Okay, people online also feel free to reply or either on chat or unmute yourself. So the question is, assuming intelligence means you can speak one full-fledged language, how does a human child learn a language?
First off, I repeat what they hear a lot, but as far as an actual understanding of what the word means, that probably takes a little more time.
Okay, so the answer in person was probably it starts with the child repeating what it's hearing, but eventually it understands the meaning of the word, right? So initially it's like, this is a word, I don't know what this is. This person is called mom, this person is called dad. If I say mom repeatedly, I get milk. If I say dad repeatedly, I get go for a walk, something. I'm making this up. But so the kid has slowly started hearing the word mom and dad, and slowly by repetition, it's understanding the meaning of it. So if I tell a 2-year-old child, let's go to the bank, what will it understand? Nothing, not a lot. It doesn't know what let's is, go is, bank is. It's expecting us to give us the meanings of these things specifically. Now, that is exactly the fundamental concept you want to think of when you think about deep learning. So when scientists were inventing deep learning, they thought, here we have a sentence, let's go to the bank. But how do you tell a machine, which is simply made out of zeros and ones, the meaning of how to go to bank, right? Let's go to bank. Or what is bank? What does bank mean? And how do you make the machine learn step by step? So if you remember last week, we had seen that deep learning is the name given to this field which uses neural networks, but that's not the real term. Why is it not neural networks? What is the actual neural network? Brain. Okay, human brain is the actual neural network, Candy. Sure. Okay. Hey, people online, you might want to start answering questions. These guys are really having a sugar high already. So the actual neural network is in your head, which is brain. And people started creating artificial neural networks. That is what we call as deep learning. And if you remember, all I mentioned was deep is just meaning the depth of the network. The more deeper it is, it's called deep learning. So then the question was, like 20 years ago, we had on one side, we had language, natural language, and people were thinking, okay, what does language mean? If you heard the name Noam Chomsky, Chomsky came up with this idea that maybe grammar is what all we need to generate a language. So he came up with these universal rules, which he said, if you use these rules, any language in the world can be created from it recursively. Here are like 3 or 4 rules. You give it a couple of initial terms, nouns, verbs, objects. Now it can start producing its own language. So in short, there was a mathematical foundation for language. Remember, why we are doing this is because computers understand only math. So tell them what language is. We need to start somewhere, right? So then my question is, when a child grows up, let's say the first few words the child learns is a mom and dad. When does it learn grammar? When does a child learn grammar? By putting things together. School, but let's say school, it by the time it reaches, let's say, first grade, the child learns officially something called grammar, but it's speaking by then, right? How did it learn the grammar? Maybe in the growing process. Okay, that's where we started with mom and dad being repetitively. Okay, with this age, what happens? Okay, the kid is processing what his family is talking about. So initially your answer was repetitive of the repetition of the word. Then it understands the meaning of the word. And then it slowly understands putting it all together. And even though it has no idea even though the child has no idea, the child doesn't know no idea what grammar is, it still is speaking well-formed sentences. It slowly learned that I want milk gives me something good. Does the child know grammar? Oh, hell no. Does it know Chomsky's rules? No, but it's already knowing this. So this is the kind of thought process which scientists started thinking. So on one side, there was language, well established mathematically. And on another side, people were inventing machine learning, like the ones you saw in your previous lecture, or even neural networks. So people started initially asking the question, okay, how do we tell machine what a language is? And some people said, okay, here, let's start with words, independent words, give them to a machine learning algorithm. So it was great. Okay, independent words, give it to a machine learning algorithm. But it failed miserably. Why? Exactly. It didn't know the meaning of it. We gave it words. We said, okay, mom, dad, give me milk. What does that mean to a machine? Nothing. It just are like binary characters at the end of the day. So then people were thinking, okay, how do we assign meaning to this? Right? That is a tricky question. Like, what is meaning? You explain to me what is meaning of mom. I don't want the definition of mom. What is the meaning of mom? No idea, right? So how do you tell? I mean, we as humans, we are able to communicate because in your head, the idea of mom is same as that in my head. The moment I use the word mom, you know what I'm talking about. How do you tell that to a machine? So initially people thought, let's hit it with everything. We'll give it all these long texts. We will even attach grammar to it, right? We will tell you this is a subject, this is a verb, this is an object. Let's give it to a support vector machine, for example. And let's see if it can classify the sentiment, right? And guess what happened? It had no idea what's going on. You just, yeah, great, a bunch of binary things combined together. What is meaning? Now, the question is, if I give you the word bank, what is the meaning of bank? Or let's say, let me ask it this way. Bank, the definition is a financial institution. Is there a different definition for bank? Can you think of anything else? Like different meaning? Bank, the word is bank. Do you use it only as a, yeah, there you go. There's an answer, river bank. Correct, so it's a river bank, right? So when the kid grows up, initially, let's say his dad tells him, let's go to the bank. So far, it has only learned let's and go is a good thing because, which means he gets to go out, right? Now, when dad says bank, he's confused. Okay, what is this bank thing? So then the dad says, oh, this is a place where we go to withdraw some cash or get cash. Good, the kid thinks, okay, this is a nice place, we get money. The next week, dad says, let's go to the river bank and get some fish. But that's not what you told me because that you don't get money from river banks. So now dad says, oh, bank has another meaning, which is river bank. I mean, granted, these explicit kind of conversations might not exactly happen the way I told you, but you get the idea, right? So the kid is slowly learning the meaning of something that was abstract became mom, became bank, became dad, and now the abstraction is getting different meanings. So what is the difference between the first word bank and the second word bank? First sentence bank and second sentence bank. When I told you, let's go to the bank to get some cash, why did your brain immediately say it's a financial institution? Cash. Beautiful. That's because we had the word cash around it. So if I say, let's go to the bank to get some fish, why does your brain say it is a river bank? Fish. So that is the key idea here. So meaning can maybe defined by the things around it. That was one school of thought, right? School of thought said, okay, we don't know the definition of meaning. We can probably tell the machine bank equals financial institution. Machine has no idea what financial institution means. So people started thinking backwards and saying, okay, wait, if bank is found with cash all the time, it always means money, financial institution. So then people started thinking, why not tell that to the machine? So that was one of the first discoveries which happened in 2013 from Stanford, where they said, okay, let's focus. Let's not worry about meaning of the word bank, but let's tell every time it occurs with cash, it has some meaning. And we're going to tell the machine that meaning is different than what happens if it occurs with river or fish, right? So that was one breakthrough human scientists had when we were trying to tell the machine what is meaning. Let's get back to the slides. So I just wanted to give this primer so that your brain starts thinking, and I did not want you to be distracted by the slides and my beautiful face. So I decided between slides and beautiful face, that's beautiful face is important, but let's see what the slides say. All right, nobody moves. Oh, quick review. If you remember, we had talked about the neural network as a constant feedback mechanism between expected speed and current speed. Then we talked about this idea called backpropagation, where the machine is trying to understand what some predicted value. You look at the difference between the predicted value and the expected value, and you backpropagate. And we saw when you do it in tons and tons of layers together called hidden layers, it becomes a deep learning framework. And when you give the whole internet as an input to the deep learning framework, ta-da, you get a large language model, AKA GPT, if you want to compare one of them. Today, we are going to learn more about transformers and more importantly, language. So this was the first question, which is how do humans learn a language? So like people arrived at the answer, which is kids start learning meaning of a word. Then there is repetition, start with repetition of the word, then the meaning of the word, and then it slowly starts building it into a sentence. So let's give an example. We start with, he keeps hearing mom, mom, mom. Okay, so it knows there's a word called mom, the child. Now the child slowly learns the word mom, and next it starts associating it with a meaning. The person right in front of me who gives me milk is mom. Now, next time when somebody says, go to mom, now the kid learns that, oh, go to mom. Maybe there was a reward function, which is, the kid got a candy every time it went to mom. So like, okay, go to mom means different thing. It's slightly an elevated level of meaning than mom. Mom, yeah, that person. The next level is humans are learning, oh, go to means something else. Same thing, right? Let's go to bank. And then the last thing is context from new examples. Let's go to bank is an example. And next time it goes, let's go to bank to fish, another example. So that's how the human learning slowly progresses time by time. And this was the kind of model which scientists were trying to get the machine to think through. But it is a hard task because like I said, the machines don't process information in the same way as humans do. If a machine says, I am hungry, it is not hungry. It is just putting three words together, I am hungry. So you see the big difference between words and meaning, right? More importantly, if there's a sentence, I am hungry, the first thing we need to do here is at least break it down into individual words, because we need to think of how can we tell the machine that, let's say the sentence is, let's go to the bank to get some cash. We need to tell the machine that, oh, this time bank occurred, the cash was next to it. Or let's say we are giving it a document about JP Morgan. So if you simply count the frequency of words, bank will be the highest, cash will be the second. So you need to first break it down to small pieces. Welcome to the world of natural language processing. And that is exactly what we do. We are trying to understand what it means for humans to be speaking a natural language. And more importantly, how do I tell that to a machine? So like I said, initially there were two major schools of thought. Technical terms are compositional and vector space based. The compositional is let's start with this. Okay, learning language from context, right? This was the second idea which we mentioned, which was given a word bank. I went to a bank to withdraw some cash, and I went to a bank and did some fishing. So this is where the school of thought or bunch of scientists who said meaning can be found from the words around it. Remember, there is no definition of meaning. What a child forms in its head is only what a child knows. How do you tell that to a machine? So, and scientists said, okay, let's tell you bank occurs every time with cash. It means money-related stuff. Bank occurs, if you're reading an article on fishing, bank occurs, highest frequency words are river, bank, and fishing. Oh, then let's call it, it's a different meaning, right? So in this school of thought, this is called the vector space school of thought. They said, let's learn language from context. So the very first thing they said, or the scientist said, was, let's take this entire big sentence. In this case, it's a paragraph, which is a movie review, which somebody says, I love this movie, it's sweet, but with satirical humor. Let's break it down and let's see which are the most frequently occurring words. And if you see, it, I, the, to, and, seen, etc. are the most frequently occurring words in any sentence. So human, especially English, is made of all these, what we call stop words. They really have no purpose because the core of the sentence, it's sweet, but with satirical humor, is satirical humor, if you think about the meaning of it, right? So it, I, the, to, etc. is really conjunctions. They're just there to like add things together. It's like glue. So scientists said, let's throw those things away. They don't have enough meaning. Let's focus on words like satirical, whimsical, bank, cash, fish. Same idea. anything, any paragraph or document you give it to the machine, this is the first thing the machine does. Break it down into small pieces and looks for which are the most frequent words that occur together. So in this case, it happens to be whimsical occurs with satirical, and they all occur only once. But you get the idea, right? If it was a bank-related document, you will always have bank or money. So to do this is what we call tokenization, which simply means take a big sentence, break it down into tokens, and the tokens is, let's say for our purpose, token is same as word. So every word is a token. In reality, it is what we call lemma, which is technically, if the word is running, we don't want to, running and run are not two different words. We're going to get it together to run. But for now, let's call words same as tokens. So this is the very first thing any deep learning mechanism does. Take the sentence, break it down into individual words. How can we do this in Python or any language? Just parse. But like I give you a sentence and I want you to give me a list back with each of these words. What will be the command you use for it? Nothing fancy. It's just a simple command, which is, okay, how is this and movie separated? Space. So if I tell the machine, just break it by space, do I get the whole list? Right? There's a dot split by space. That's all you do. Dot split by space, you get a list of each word with space, each word without a space. This ignore space movie. That's all tokenization is. Now there are fancy algorithms to do it, but fundamentally, that's all it does. Takes the big sentence, breaks it down into small words. And this is exactly the next step, which is let's count the number of times the word occurs. This movie is very scary. As we saw earlier, is what we call a stop word, occurs 2 times. But you get the idea, right? This is how we start counting and telling the machine, hey, these are the words that occur too much, is, the, it, this, etc. Ignore them. But here are some words which actually contains the meaning of that sentence. Very scary. This movie is very scary. So if you think about that sentence, when somebody tells you this movie is very scary, you go home not with this, not with movie, but the idea of very scary. And those are the words which don't occur that frequently. So this is the kind of thought process people had. Okay, how do we tell this to machines, right? And now this is called, like I said, vector space models. And when people started counting the number of words that occur close to queen and king, and even woman and man. So basically, let's say you give it a big textbook of human nature or even mythology, right? Give a big textbook, and when you started plotting this, we realized that all the words that occur next to king and queen, the distance between those 2 words is exactly the same between man and woman. So that's when the scientists realized, oh, maybe that is a way to tell machines who is a king when in comparison to queen. A king is a person whose vector is 2 degrees away from queen. Okay, so given that, how do you tell the machine what a man is? Oh, it's simple. We tell, given the vector of woman, go 2 degrees to the right, you will find man. So you see the big pattern there, right? When people started counting the words around one given word, we slowly started finding patterns of meaning that come together. Like king, queen is king's wife or king's partner. A man is a woman's partner. But when you plot it all together, you realize, oh, it's the same angle between these 2. So the machine is learning something. Machine is telling you there is this abstract concept by which you can define a king and queen, which is his angle. So that was one of the nice tricks that scientists came up with, saying, okay, maybe that is meaning, right? So meaning is essentially, king is defined by queen, who occurs most frequently with him. Queen is defined by king. And they even found that you can, if you want to get to the vector of queen, all you have to do is take the vector of woman, add king to it, and subtract man from it. And you automatically reach the angle of the queen vector. So when that discovery happened in 2013 in Stanford, people said, oh, you know that oh feeling you got just now? Oh, this is exactly how we can tell machine what queen means. This was the other school of thought, which says compositionality, where not only we will just give it all the tokens or words, but now we'll start telling grammar. This is a subject, root, object, determiner, modifier, blah, blah, blah. And the machine said, I don't know anything what you're talking about. It's all tokens to me. It's all words to me. And more importantly, just for a sentence made out of 7 words, the sheer number of grammatical terms which we had to add to the machine was huge. And support vector machines and all the good old AI, what we call machine learning these days, they just gave up. They're like, one, we don't have hardware support for it. It's just information. So it just failed. So originally that was the original idea, but then people went back to the vector space models. And now everything neural network, everything transformers is based on vector space models. Now, in a nice twist of fate, right now there is quantum NLP, QNLP, and it is going back to the original where what we do is we take vector space models for meaning, and then we give it to grammar. So but you see the big picture, right? How do humans tell another human what meaning is? So I'll just run through this. Like these are the typical tasks in NLP, which is now these days in NLP, you give a whole sentence, it can classify it, sentence, email. For example, you give it an email, it can filter and tell you whether it's a spam or a good email, right? Oh yeah, this is the Nigerian prince, the lady saying, oh, that Nigerian prince never emailed back, hope he's okay. So if you know the story, there is this huge scam that happened 20 years ago where a Nigerian prince says, oh, I'm abdicating. Like everybody gets an email. I'm abdicating. I have a lot of extra money. You give me your bank account. I will send you the money. So a lot of people send the bank account and next thing you know, that is hacked. So exactly this world of phishing and emails. But that's why we have inbox and spam, right? So natural language processing helps you do that. So you can classify a whole sentence. You can generate the text content, which is exactly what GPT gives. You ask a question, it generates the answer and gives you back the text. And right now we have all these great models which do all that. All right, so like I said, this is all transformer-based stuff. Let's get our hands dirty. So let's go to the DL Deep Learning UA Data Lab, GitHub, if I can find it, U Arizona Data Lab, repositories, DL workshops, intro to transformers, which we almost had an intro last week. Today, we're going to see how we can take everything we learned and put it to practice. Okay, click on Open in Colab, like last time. Okay, this opens the existing code, which I don't want you to use. This is for you to look at it once the class is done. What I'm going to do now is I'm going to create a new notebook, and I want you guys to create a new notebook. And the very first thing here, this is exactly what we did last time. From transformers import pipeline, and we give it pipeline, give me sentiment analysis. We give it 2 sentences. First one was, I've been waiting for a Hugging Face course all my life. That the machine said the sentiment is positive. And the next one, I hate this so much, the machine says the sentiment is negative. So we saw this last time. Now, this time, what was the first thing I said that a machine does? Let's say this movie is scary. So what is the first thing we do? when a deep learning network is presented with this sentence? Break up the words. Okay, good. All right, let me move this. Okay. All right, break up the words. Okay, candy. I think, do you get the red one yet? All right, so what we do is let's call it like send, right? Send equals, so print send dot split. I think by default, if you just print send dot split, it will break it based on the words and give you a list of words. Ta-da, ta-da, if it works. All right, so this is the very first thing it does. Let's break it into small words. But these days, there are a lot of fancy algorithms to do it. So let's do the fancy way, which is there is an AI model these days for every single task you can think of. So for this, the task is called, the model is called tokenizer. But before that, we need to do something. Pip install something. What was it? Transformers. Yes, pip install transformers. Let it do its thing. I hope you guys are following with me. And once you have the transformers, the thing we need to get from transformer, it's called auto tokenizer. So from transformers, import auto tokenizer. Okay. And basically you import a class auto tokenizer and we initialize a tokenizer. Let's call it tokenizer equals auto tokenizer. Let's copy paste. There you go. Smart. Auto tokenizer. Let's see what happens. Let's run this. Should give you an error, maybe. Yep. Its error is basically, oh, auto tokenizer, you need to tell me which model do we need to use. If you remember from last class, everything has a model. There's a tokenizer model. So if you don't know what model to use, huggingface.co/models, let's call it GPT. Or, yeah, I don't know if this will work as a tokenizer. We'll find out. It's probably more complicated than, so all you do is give the name there, the exact name here. Yeah, okay, this needs more arguments. I'll just put a simple one, which is call it Distilbert. This is like the very starting Distilberts. Yeah, this one. So it's called Distilbert. Guys don't need to know. This was one of the initial models which came out. It based on BERT, which is another term for transformers. So let's use that as a tokenizer. Still doesn't help. Oh, it doesn't. Never mind. 1 second. Let's just call it this. Oh, because I'm giving this whole thing, it doesn't understand the whole thing. That's probably the mistake last time. So we had to just give it this name. Nope. This. All right. Getting there. Nope. Let's see. Need to be exponentially mentioned. Let's see. Transformers. All right. Checkpoint is Distilbert. What did I miss? Tokenizers. Oh, yeah. Okay. This is what it was saying from pre-trained. It needs to be from pre-trained. And that essentially means all these models are already well trained to understand these tasks. So here it's, if you can read this model, it's called Distilbert. It's uncased, which means it doesn't matter uppercase or lowercase, it will still do the job. And its SST actually stands for sentiment analysis. And that we are going to do that task again today, but with more complicated models. And it's tuned for English. So all we do now is give it a tokenizer from pre-trained checkpoint. And it says, oh, I have a tokenizer ready to go. So let's see if this works, right? We will call tokenizer. Where is let's have a sentence here. I'm going to create a sentence. sent equals this movie was scary, exactly what we saw earlier. And let's see what happens if we just give the sentence print tokenized. All right, it does kind of the same thing, but it takes it another step ahead, which is it assigns unique values for each of these terms. So just a fancy way, you don't have to worry what an attention mask is. So that's all you need to understand, that this is called, this is the very first step any model does, which is let's break it down into sentences. And in this case, it is more fancier because it needs to uniquely identify the word. So once you have this sentences or tokens ready to go, the next thing you do is from transformers, import auto model for sequence classification. So right now, I know this is all new terms to you, but just Google Hugging Face auto models, auto classes. It'll tell you auto models and auto classes, where essentially you're just taking a pre-trained model, exactly like we did for tokenizer, but this time, this is the classification model, which will classify your sentence sentiment into positive or negative, right? So let's go back. So we have from transformers import auto model sequence for classification. And its idea is still the same, right? Here, the model, instead of, here we said auto tokenizer dot from pre-trained. Now all we do is auto model for sequence classification dot from pre-trained. And you can use the same, let's call it model name, model name, model name. Okay, so let's see if this understands model name. From transformers, we got a tokenizer. It has a model name Distilbert. We're going to use the same tokenizer. That's it. So this model is right now ready to go. It is specifically trained for sentiment analysis, which is why I picked that model. And we need to find out the sentiment of this sentence. In fact, let's give it two sentences. I'm going to call this in a two sentences. Let's call it lists. Okay. Let's make it more easy. This, I hate this movie. This movie. And second one is, let's call it, I love this movie. Maybe I'll give the positive one first. Doesn't matter. I'm just keeping it, trying to be positive first. No pun intended. All right, so we have this. We have the input ready to go. We have the model ready to go. And all you need to do after this is just say model of inputs. Essentially means we take the model and run it on the inputs. Let's do outputs equals model of star inputs. If you're familiar with Python, it's just a way of passing more than one arguments. So all you have to do is, so we are done with the sentiment analysis model without a pipeline. And remember, the whole idea is we are learning this step by step, starting with the easiest way, which is the pipeline. And this time we are saying, oh, let me make it more complicated and see if this works. Because now, slowly, I'm giving you the tools, which is, one second. This is probably not remembering it from the previous slide. Oops, this is the inputs, is tokenizer sentence, input, never mind. Inputs, prints the inputs. So you created the auto model, outputs, model, star inputs. Interesting. Okay. Weird. All right. I'm gonna this time copy paste the stuff from what works and try not playing around with it on the fly. So nope, not tokenizer. The other one, inputs. You can go back to the page I showed you earlier and the code there works. All right, so let's copy paste there, which is model inputs, work. Nope, inputs is still, oh, I know what happened. Okay, so there were a lot of fancy stuff we had to tell it for the input tokens here. When I was teaching you, I just ignored all the fancy stuff, which is raw inputs, padding, truncation, etc. These are like extra bells and whistles you need to give the model during tokenization, just like, okay, hey, this is the kind of things we want you to do, including like, if when in doubt, pad it with zeros. Let's say the first sentence is 10 words long, the second sentence is only 5 words long. So what do we do with the rest of the words? Just pad it with 0. That's all. Padding is true. Truncation is true if it is way beyond a number. Like, let's say the max length is 100. If the sentence is more than 100 words, we just stop it, ask it not do it. Okay, so this is again from the earlier thing. We are just from transformers. Hold on. I am a mess today when I should just directly use what they have. Okay, from transformers import tokenizer, we are giving it the correct tokenizer. We are giving the raw inputs and we are giving the tokenizer and printing the inputs. So it's working fine. So now we go back to the same page where we have, just gonna move this guy away. I'm shamelessly copy pasting from the slide, which is from transformers, import auto model for sequence classification. Okay, finally, I'm guessing it's basically the inputs needed all these funny things with it and it understands the model. So let's see so now our task is done. All you have to do is print output and it's gonna say, oh, let's see what it says, print output. Okay, so it's a bunch of numbers. Remember, machines don't understand language, it understands only numbers. But let me explain to you what this means. Sequence classifier is trained to identify 2 sequences, positive or negative. In fact, if you exactly want to know which is what, you can type, let's say, model.config.id to label, and it'll tell you that I am trained to do 2 things where 0 is negative. Whenever I think the sentence is negative, I call it 0. Whenever I think the next sentence is positive, I call it 1. But even that, the machine has a weird way of telling you. It doesn't exactly tell you straight on your face, but instead it says, hey, here are the confidence values for each of these labels. So the way you read this is, the first label, negative, for the first sentence, I have been waiting for a Hugging Face course all my life. For the first label negative, it has a negative value, which means it's not a negative sentiment, but the highest value is the positive sentiment here. And for the second sentence, I hate this so much. So let's do a good way of getting it out of there. So, okay, so now we have the model. We have the sentiment out of it. So to remember this thing which we were doing is looking at the output and deciding which one is the machine actually telling you the sentiment is. There's a tool called softmax over it. And what softmax does is puts it in a nice probability distribution. Again, you don't need to know all that. Basically giving it in a nice way so that you have a good output. And still remember, we have only numbers. We don't know how to get a sentiment out of it. So let's see. Let's try what are the predictions, right? So out is equal to predictions dot to list. Okay, so now the predictions is the same values which you saw here is the weightage or the percentage weightage. which the model is saying, I think this label is bad, this label is good. Second case, first one is good, second one is bad. So essentially it is saying first label, negative, is it thinks is correct, the higher the value. And if you go back to sentence, the sentence is, I hate this so much. So it's negative. So the machine is doing a good job. Now, all we need to do is try to print it in a nice way so that humans can understand it. Let's do let's enumerate through this. I'm assuming you guys are familiar with this Python syntax and code. I'm not going into what enumerate is. So I want to find out what is the index of the maximum value. For example, given if the machine is telling me, hey, here is my confidence for the first sentence, where I give the maximum value to the second label, which is, in this case, is positive, right? So I take the index and I ask it, given the index, so let's print the index first. Let's see what index is, right? Okay, so the first one, it says, remember, array starts with 0 and 1. For the first one, it said, oh, I think this is the one which has the highest value, which is correct, index of 1. And the second one, index of 0, has the highest value. Now, remember, we have this model to config.id to label, which is essentially a dictionary which will tell you, given an index, what is my corresponding textual value. All right, there you go. So all it's telling you is first sentence is positive. Let me also print the original sentences, right? So what is the original sentence? Print raw underscore inputs. Inputs, we don't want to print the index again. All right. It says the machine is already saying, hey, this first sentence is positive, second sentence is negative. So last week, we saw how to use a pipeline to do this task. But now, as you can see, we are learning more tools inside it, which is helping you come up with a sentiment. Now, why am I making a big deal out of this? The deal is tomorrow, if you want to try another model, all you have to do is change this value, checkpoint, call it GPT. It might seem pretty simple as of now, but next, when we come to complicated tasks, you will realize like GPT kind of bigger models have better power to answer all your questions correctly. And the lower, especially like in generation tasks, you will realize that GPT can generate better words, which is clearly why ChatGPT is famous. Okay, so let me quickly also go back and finish my slides. I think there were a couple of slides which were left. Yeah, never mind. It's basically just saying how do transformers work. These are a few tasks for causal LM. And these days it takes a long time to train all these models because, we have to give it all these sentences because for the example of bank, we have to tell the machine all the occurrences of bank with the words around it. So that is essentially why we have to do that. I was not, okay, what screen am I sharing? Not this screen, is it? All right, never mind. Either way, we are done with the class for today. Go home, play around with this stuff and see what you see there.